Five assets produced one period returns of 1, 2, 2, 3, and 22%. Ask a data analyst for the average, and the answer is 6%. Ask the portfolio manager, and the answer is 2.9%. Ask for the middle performing asset, and the answer is 2%. Did two calculators fail? No. The people answered different questions while using the same data. This video is about choosing the question before choosing the average. The subject is not a competition to crown one perfect average. Arithmetic mean asks where the observations balance under equal counting influence. Weighted mean asks what the average becomes when influence comes from capital, probability, volume, or another declared weight. Median asks for the middle rank. Mode asks what repeats. Later, we will also see how trimming and Winsorization reduce tail influence without pretending that unusual observations never existed. First, we will define exactly what each row represents, which period is measured, and why the portfolio weights must come from the beginning of that period. Each observation represents one asset measured over the same single period. Asset A returned 1%, B returned 2, C returned 2, D returned 3, and E returned 22%. This is a cross-sectional comparison, several assets during one period. It is not one asset moving through 5 consecutive periods. That distinction matters because this video is about location across observations, not compounding through time. The portfolio begins with weights of 30, 25, 20, 20, and 5%. They add to 100%. We use beginning of period weights because those exposures existed before the returns were realized. Using weights calculated after the period can allow future performance to influence the historical calculation. In code, store the returns as decimals, 0.01 through 0.22, and convert them to percentages only for presentation. We will begin with the familiar average and see why equal counting influence does not mean equal numerical impact. Arithmetic mean treats every asset as one observation. Asset A receives one counting vote. Asset E also receives one counting vote, but equal counting influence does not make the return magnitudes equal. The 22% observation contributes 22 points to the sum, while the 1% observation contributes only 1. One asset gets one seat, but the number written on its card can still be very loud. Add all 5 returns. 1 plus 2 plus 2 plus 3 plus 22 equals 30. Then divide by the 5 observations. 30 divided by 5 equals 6. The arithmetic mean return is 6%. This describes the average security when every asset receives equal counting influence. Another way to understand the mean is as a balance point. Measure every observation's signed distance from 6. The 4 lower observations contribute negative deviations. The 22% observation contributes a positive 16-point deviation. The signed deviations sum to 0. The large value pulls the balance point toward itself, which is why arithmetic mean responds strongly to extreme magnitudes. Next, we will stop adding magnitudes and instead ask 2 different questions. What sits in the middle and what repeats? Median begins with order. Sort the observations from smallest to largest. In this example, they are already 1, 2, 2, 3, and 22%. Assign ranks 1 through 5. With 5 observations, the median is the value in position 3. The median does not average the 2 sides. It identifies the middle ranked observation. The third observation is 2%, so the median is 2%. Notice what did not enter the calculation, the distance from 3 to 22. As long as the extreme value remains on the same side of the ranking and does not cross the middle, its exact magnitude does not change the median. Median is therefore resistant to tail magnitude, but it also discards much of that magnitude information. Mode asks which exact value occurs most often. 1% appears once, 2% appears twice, 3% and 22% each appear once. The mode is therefore 2%. This can be useful for repeated discrete outcomes or rounded categories, but in continuous, high-precision financial data, exact repetitions may be rare. Changing the rounding precision can create or remove a mode. We will now replace equal counting votes with actual portfolio exposure and calculate the return of the invested portfolio. The arithmetic mean asks about the average asset. The portfolio manager needs a different answer. What return did the actual portfolio experience? Asset A represents 30% of the starting capital. B represents 25. C and D each represent 20. Asset E, the 22% winner, represents only 5%. A large return on a small position can matter less to the portfolio than a modest return on a large position. Multiply each return by its beginning portfolio weight. Asset A contributes 0.3 percentage points. B contributes 0.5. C contributes 0.4. D contributes 0.6. Asset E contributes 1.1. Add the 5 contributions and the portfolio return is 2.9%. If every asset receives an equal 20% weight, the weighted mean becomes the arithmetic mean, 6%. But the arithmetic can be correct while the weights are economically wrong. Capital weights, probabilities, volumes, market values, and importance scores do not mean the same thing. The values and weights must align, and their total weight cannot be zero. A dollar-neutral long-short portfolio needs a separately defined exposure or contribution method rather than this ordinary weighted average interpretation. We will now change one observation. Predict which measures will react and compare 3 different ways of limiting tail influence. Asset E's return changes from 22% to 60%. Nothing else changes. Its portfolio weight remains 5%. Before calculating, predict the response. Will the arithmetic mean move sharply? Will the weighted mean move by the same amount? Will the median or mode change? And what happens to the trimmed and Winsorized means? The arithmetic mean jumps from 6% to 13.6% because the 60% magnitude enters the equal count sum in full. The weighted mean rises from 2.9 to 4.8%. It moves, but less dramatically, because asset E still represents only 5% of the portfolio. Median remains 2% because the middle rank did not change. Mode remains 2 because the repeated value did not change. The chosen trimmed and Winsorized means also remain unchanged. A 20% trimmed mean removes 20% of the observations from each tail before averaging. With 5 observations, that means removing 1 value from the lower tail and 1 from the upper tail. Remove 1% and 60%. The retained values are 2, 2, and 3. Their mean is approximately 2.3333%. Winsorization keeps all 5 observation slots, but limits the tail values. Replace the lower 1% return with the nearest retained boundary, 2%. Replace the 60% return with the upper retained boundary, 3%. The resulting values are 2, 2, 2, 3, and 3. Their mean is 2.4%. Trimming and Winsorization are not automatic outlier cleaners. They are declared statistical policies. A surprising observation may be bad data, a stock split, a unit mismatch, a duplicated record, or a genuine market event. Investigate first. If the observation is valid, removing or replacing it changes the question being answered. The tail policy must therefore be visible, reproducible, and justified. We will now connect each measure to the financial problem it is actually designed to summarize. Use arithmetic mean when each observation should receive equal counting influence. For example, the average return across a chosen set of securities. Use weighted mean when observations represent different economic exposures, probabilities, volumes, or sizes. Use median when the middle rank is more informative than the tail magnitude. Use mode when repetition itself matters. Use a trimmed or Winsorized mean when a mean-like measure is needed, but the tail policy must limit endpoint influence. In portfolio return, weights may represent beginning capital exposure. In expected value, the weights may be probabilities. In VWAP, trade prices are weighted by volume. In a market cap weighted index, constituent influence is related to market capitalization, but the word weight is not enough. Capital, probability, volume, shares, and market value have different units and meanings. A production index also needs divisor and corporate action rules. It is not merely one weighted average formula. We will finish by navigating the 4 canonical Fintech builder lessons, running the package, and turning the result into a repeatable decision framework. On the fintechbuilder.com, begin with arithmetic mean. Highlight the equal influence definition, the formula, the balance point interpretation, and the guided example. Next, open weighted mean. Highlight aligned values and weights, the non-zero weight sum rule, and the portfolio contribution breakdown. Continue to median and mode. Show the sorting step, the middle rank, the frequency count, and the exact equality boundary. Finish on trimmed and Winsorized means. Highlight the difference between removing tail observations and replacing tail values. Then open the Guided Lab and Implementation tabs. The source pinned implementation uses decimal returns and beginning portfolio weights. Install the recorded package version, import the 4 canonical functions, and pass the same values used in the visual example. The arithmetic mean should return 0.06. Weighted mean should return approximately 0.029. Median and mode should return 0.02. The robust function should return approximately 0.02333 and 0.024. Convert to percentages only in the presentation layer. Correct code still depends on a correct data contract. Values and weights must align. The weight sum cannot be 0. Signed weights can produce a result outside the observed minimum and maximum. Mode uses exact equality. The current runtime also coerces entries through JavaScript's number conversion, so values such as null or an empty string may become 0. Validate external data strictly before calling the functions. And remember, a mathematically correct weighted mean with economically incorrect weights is still the wrong financial answer. Use this decision sequence. First, are all observations comparable and measured on one declared basis? Second, should every observation count equally or should influence follow a weight? Third, do you need magnitude, rank, repetition, or a mean with reduced tail influence? Fourth, what do the weights represent and when were they known? Finally, how will missing values, extreme observations, rounding, and validation be handled? Final quiz. Asset E moves from 22% to 60% while retaining a 5% portfolio weight. Which measure moves the most? Which moves but less? And which remain unchanged? Arithmetic mean moves the most, rising to 13.6%. Weighted mean rises to 4.8%. Median and mode remain 2%. The selected trimmed and Winsorized means remain approximately 2.33 and 2.4%. We now know several ways to describe the center. The next question is position. Is a return near the bottom, the middle, the top quartile, or the 95th percentile of the dataset? That is video 007, Percentiles, Quartiles, and Quantiles explained with market data.